Okay, so welcome to the next session, um, TA session number 7 on this NPTEL course, Principles of Signals and Systems, offered by Professor Aditya Jagannatham from IIT Kanpur. My name is Yashvanth, and I'm a PMRF Ph.D. student at the Department of EC at IISc Bangalore. My broad research interests lie in signal processing and wireless comm systems, and particularly in the technology called intelligent reflecting surfaces for 5G and beyond wireless. You can email me if you have any doubts on what the sessions that we take, that is, any doubts in the contents that I deliver in these sessions. And the topic that was covered for this week, week number 7, will. Are you able to hear me? Just to confirm.
Yes, sir.
Okay. Yeah. So the topic for this week will be on Fourier transforms. Okay. So Fourier transform is a very important topic as far as this course is concerned, because there are varieties of applications of Fourier transform. So it's very important that we understand Fourier transform. It's used in many applications like image processing, or you go to speech processing, or you go to, let's say, even wireless communication systems. You take any number, any application. It's very easy to find any kind of technology. It's very easy to find some applications of Fourier transforms. So Fourier transform is very important. Okay, so yes, so we will be doing some problems related to Fourier transforms, also Fourier series. Okay, so as usual, the first part of the session will be to quickly summarize what has happened in week 7. Okay, so week 7 started with the notion of Fourier transform. So what are Fourier transforms? Fourier transforms are basically another way to represent the same signal, but in a different domain called the frequency domain. So recall that Laplace transform, what it did is it took your time domain signal x of t, and then it is basically representing the same signal x of t in a different representation, in a different domain called Laplacian domain, and that would denoted by x of s. Similarly, instead of the domain called Laplacian domain, if you represent the same signal x of t in the frequency domain, that is called Fourier transforms. It's x of f, where f is the actual frequency in hertz, or you can say angular frequency x of omega, where omega is related as 2 pi f. Okay, both are synonymous. I mean, both are equivalent. You can always establish equivalence between two domains. So Fourier transforms are basically defined for continuous time aperiodic signals. So recall that Fourier series was for continuous time periodic signals, but Fourier transform generalizes it to even aperiodic signals. So Fourier transforms are very important. So we will spend quite a good amount of time on solving problems of Fourier transforms and Fourier series also. Okay, so how was Fourier transform defined as? You take the signal x of t and you multiply by e power j minus j omega t and integrate it from minus infinity to plus infinity with respect to the time variable t dt. And whatever is the value that you get is called x of omega. So for different omega, use different omega in this here and then evaluate the integral. That will be the value of x of omega. Right. So this is basically how Fourier transform is computed. So if so, here omega is called the frequency variable. But let's say if I define a frequency to be just f, then this is how the definition is. Essentially, what you do is you replace omega by 2 pi f. Then evaluate this integral. Whatever is the value you get, that is basically the Fourier transform. Okay, you can use both of these synonymously. There's no problem. Just that they will differ by some constant 2 pi. Okay, but except for a constant 2 pi, both the results will be identical. Okay, so you can stick with any of the definition, no problem. Depending on what is being asked in the questions, whether they ask for omega or they ask for f, accordingly you choose whichever definition you have to follow. Okay, so representation of the time domain signal in the frequency domain is a Fourier transform. Similarly, inverse Fourier transform, what? Basically, you're given a time frequency domain signal. How do I go back to time domain signal? So here you take the frequency x of omega and multiply by e power plus j omega t and integrate with respect to omega from minus infinity to plus infinity, and then multiply it with 1 by 2 pi. Whatever is the answer here, that is basically your x of t. Or if, in other words, if someone gave us x of f instead of x of omega, Then you multiply this by e power j 2 pi ft df, e power j 2 pi ft df, and integrate from minus infinity to plus infinity. There is no 1 by 2 pi constant sitting here. Okay, fine. Okay, so now this is basically the definition of Fourier transform. Now associated, just like Fourier series, for a Fourier transform also you have the notion of what is called a spectrum. Okay, so what is a spectrum? Spectrum is nothing but it basically can be decomposed into, basically it's a Fourier transform only. So Fourier transform is nothing but the frequency domain representation. So spectrum, if you recall from your high school, spectrum is the term we usually denote for frequency components in a signal, right? That's why Fourier transform is also called the spectrum of a signal, and in turn it has two components. One is called the magnitude spectrum, the other is called the phase spectrum. In magnitude spectrum, what we essentially do is we compute the absolute value of x of omega for different omega. So for example, if I plot omega, mod of x of omega as a function of omega, some graph you will get. This is called the magnitude spectrum. Okay. Similarly, if I take the angle of the Fourier transform, see, go back to the definition of Fourier transform. So e power j omega t is a complex number. Even if x of t is a real number, the multiplication of x of t with e power minus j omega t is a complex number. So essentially you're doing a complex integration. So output should also be a complex number. So essentially Fourier transform is a complex valued function. Okay. So therefore it has a real magnitude part and a phase part. So now if I plot the phase of the Fourier transform, that is angle of x of omega with respect to omega, I will get some graph. This graph is called phase spectrum of the signal x of t. Now for a real signal, that is x of t is equal to x conjugate of t. In the time domain, it's if the signal is real, then similar to Fourier series, recall, similar to Fourier series, for Fourier transform also we have an equivalent property, that is x conjugate of omega will equal x of minus omega. Okay, so that is you do a conjugation to x, that is same as whatever value you get for the the transform x of omega, but at evaluated at omega equal to minus omega. Okay, so x conjugate of omega is equal to x of minus omega. This is called conjugate symmetry. Okay, this is called conjugate symmetry. So based on this, so what does it mean that? So if I take the magnitude on both sides, let's say I take mod on both sides, what does it mean? But mod of xr of omega is same as mod of x of omega, because conjugation doesn't change the magnitude. That's why for a real signal, you have mod of x of omega equal to mod of x of minus omega, which means the magnitude spectrum follows the even symmetry. What is even symmetry? X of t. If you remember, even signal is a signal where x of t equal to x of minus t. Similarly, you can define for any function. If you have f of x equal to f of minus x, this is an even function. So now this is basically a function in omega following the trend that mod of x of omega equal to mod of x of minus omega. So this magnitude spectrum function follows the even symmetry. Similarly, if you take the angle on both sides for this equation, we know that if you conjugate, the angle will flip, right? Because what do you mean by conjugation? Let's just take an example. If I have, let's say, a plus jb, what is the angle? Angle is nothing but tan inverse b by a. This is the angle of the complex number. Now, if I conjugate it, then it becomes a minus jb. What is the angle? Tan inverse of minus b by a, or is equal to minus tan inverse of b by a. That is basically, it is a negative of the angle of the complex number a plus jb. So whenever you take a conjugation, the angle will become negative. You should take the negation of the angle. Okay, so that's basically the reason of behind this odd symmetry. Okay, basically that if you take the phase spectrum of your signal x of t, then they will follow an odd symmetry, namely that angle of x of minus omega will be equal to minus x minus of angle of x of omega. Okay, this is basically called the odd symmetric nature of your phase spectrum. Now, some conditions, when will Fourier transform integral exist? Similar to Fourier series, we have what is called the Dirichlet conditions for convergence. What is the convergence here? Convergence is whether this integral, right? This is an integration. This can go to infinity, it can diverge, or it can converge to a finite number less than infinity. If it converges, that means we generally say that whenever we talk about convergence, we generally think about that this is going to tending to some finite number c, which is less than infinity. Now the question is, when under which conditions will this Fourier transform or this integral converge to some finite number? Right? That is basically called that is given by the Dirichlet conditions. Okay, that is, these are the three conditions very similar to what we had for Fourier series. First condition says that your x of t should be absolutely integrable. Second condition says that your x of t has finite maxima or minima. What do you mean by absolutely integrable? You take the function x of t, apply modulus, and then integrate with respect to t from minus infinity to plus infinity. If this integration is, if this number comes out to be a finite number, then x of t is said to be absolutely integrable. Okay, that's the first condition. Second condition is x of t should have finite number of maximas or minimas. And third condition is that x of t should have finite discontinuities. If these three conditions are satisfied, if these are the three conditions for which we call it as Dirichlet conditions, and if at least one of these three conditions is satisfied, then we can always guarantee that Fourier transform will exist. Okay, that is, these give us a sufficient conditions to establish whether the Fourier transform of a signal will exist or not. These are sufficient conditions. Okay, now one quick thing I would like to mention is that the Fourier transform has a it has one similarity with the Laplace transform. What is it? The Laplace transform evaluated at the complex number s is equal to 0 plus j omega gives the expression for Fourier transform. Basically, what I'm saying is, you recall that Laplace transform was for a complex number s, which can be represented as sigma plus j omega. What I'm saying is, you put sigma equal to 0 and just evaluate the Laplace transform at j omega. Whatever is the answer you get, that is basically the Fourier transform. Okay, it's a very informal statement, means it's not a very very concrete statement, but most of the problems you will see that whatever is the answer you get for Laplace transform, put s is equal to j omega, that will give you the Fourier transform. Okay, for it, why do I say that? Because you go back to the definition. Okay, this is the definition of our Fourier transform. Now recall the definition of Laplace transform. Laplace transform was what? X of, okay, maybe I'll go back to the first definition. X of s is equal to minus into infinity to plus infinity x of t e power minus st dt. This is the Laplace transform definition. Right. Now let me put s is equal to 0 plus j omega. Okay, then right hand side is nothing but x of j omega equal to minus infinity to plus infinity x of t into e power minus j omega t dt. Of course, left hand side is just a function. You can denote it however you want. You can say either f of x or you can say f of x dash. This is a dummy variable. So you can again call this as x of omega. No problem. What matters is the value. See, the value is exactly same as the definition of your Fourier transform. That's why most of the times, okay, this should be you should be very careful in applying this. You can do this only if ROC includes the unit circle. Okay, see, basically what it says is that if the Laplace transform, sorry, not the unit circle is for Z transform, right? Okay, includes a j omega axis. Okay, if for the Laplace transform, the whatever ROC you get, right, if that ROC includes, that is j omega axis is a part of your y axis is a part of the ROC, then just you substitute s is equal to j omega, whatever is the value you get, that will be the Fourier transform. Okay, this is basically the condition. If this is satisfied, then basically if it is enough, if you know Laplace transform, you can just substitute s is equal to j omega and you'll get the value for Fourier transform. Okay, so this is one similarity that Laplace transform and Fourier transform shares. Okay, why I'm saying this is you will now see that the properties of Fourier transforms essentially will be very, very similar to what the properties that we have seen for a Laplace transform. So let's look at the four properties of Fourier transform. So the reference from which I've taken this table is from the textbook on Signals and Systems by Oppenheim, chapter number 4. Okay, this is table 4.1 in this book. So Basically, let's say x of t is a periodic, it's a periodic signal, and its Fourier transform is x of j omega. You see here, this book uses the variable j omega in the argument itself. Okay, so it's just our it's just our convenience. You can either write x of j omega or x of omega. Doesn't matter. What you should, where you should be careful is in the value of the integral. So here you should be very careful to include j omega. This the inside the integration you should be careful. It doesn't matter how you denote. You can write this anyway. It's just a notation. But this integral value should be correctly written. Okay, let's now go back to this property table. So let's say x of t and y of t have the Fourier transforms x of j omega and y of j omega. The first property is a linearity property. So what it says is that if I do an operation a times x of t plus b times y of t, then the corresponding Fourier transform will be a times x of j omega plus b times y of j omega. Okay, similar to Laplace transform. Next is called the time shifting property. If I time shift the x of t by t naught, that is x of t minus t naught, will have the corresponding Fourier transform x of minus e power minus j omega t naught into x of j omega. See, this is also similar to Laplace transform only. In Laplace transform, we say that x of t minus t naught will have the Laplace transform e power minus s t naught into x of s. Now just put s is equal to j omega, you will get this result. Okay. Next, frequency shifting property. What is frequency shifting? If I multiply by an exponential signal in the time domain, that is e power j omega naught t into x of t, that will have the corresponding Fourier transform x of j omega minus omega naught. This is again similar to Laplace transform. In Laplace transform, what did we see? E power j yeah, e power s t naught, right? Or no, sorry, e power s naught t times x of t will have the corresponding Laplace transform x of s minus s naught. Right, this is what we saw in Laplace transform. Now put s is equal to j omega and s naught is equal to j omega naught. What is the value? That's a frequency shifting property. Now conjugation, similarly x conjugate of t will have the Fourier transform capital X conjugate of minus omega. So there's two things: you conjugate and also do a minus and reversal of the omega variable. Both you do. Now time reversal. Time reversal means you do x of minus t, that will have the Fourier transform a capital X of minus j omega. Then frequency time and frequency scaling. What it says is that if let's say x of t has a Fourier transform x of j omega, then x of at, right? Recall what does this do? It does time scaling. If a is greater than 1, then it is a compression. If a is less than 1, it's an expansion. We saw that in the first few classes. So x of at, okay, maybe, or if not, I will give it an example of how x of at you can do. We will do that one example now. So x of at will have the Fourier transform 1 by mod a x of j omega by a. So you see that a was multiplying t in the time domain, but in the frequency domain a is dividing omega axis. Right, so here it comes at, but here it comes omega by a. It doesn't come as a omega. No, it comes at omega. It comes as omega by a. Instead of product, it divides. So basically, what does it mean? It means that if I have a compression in the time domain, it will have an expansion in the frequency domain. Or if I have an expansion in the time domain, I will have a compression in the frequency domain. That's basically the interpretation. If I multiply by t a in the time domain, I will divide by a in the frequency domain. Similarly, if I divide by a in the time domain, I will multiply by a in the frequency domain. Okay. Next is the convolution property. Convolution property states that if I convolve two signals x of t and y of t in the time domain, their corresponding Fourier transform will just get multiplied. Same as Laplace transform, right? There also we told that convolution of two signals will have its Laplace transforms getting multiplied. Now, what happens when you multiply two signals in time domain? What happens is convolution will happen in the frequency domain. So it's a very nice property. You see, if I convolve two signals in the time domain, then their corresponding Fourier transforms will get multiplied. If I multiply two signals in the time domain, their corresponding Fourier transforms will get convolved. So it's a this is called, basically this is a very interesting property that we will use in many applications, especially in what is called the duality property of Fourier transforms. Duality property is very, very, very useful, for the reason that this integration, right? If the x of t is very difficult, it's not very easy to compute this integral. You might not be able to find out the value for the integration. It's not very easy. But using these properties of Fourier transform, we can relate one signal to another signal and easily derive the Fourier transform using the properties. Okay. I'll tell what duality is also. Now, similarly, we have multiplication, then differentiation. If you differentiate d by dt of x of t, we'll have j omega times x of j omega. This is same as Laplace, right? What did we have in Laplace? We told that d by dt of x of t, the corresponding Laplace transform will be x s into x of s. Put x s is equal to j omega. That is basically this. Okay. Similarly, if you integrate, you will have s coming in the denominator. If you differentiate in frequency, then basically the corresponding time domain signal is t into x of t. I think all these things we have seen in Laplace transforms also, right? Then then there are some summarized properties. If x of t is real, then how will the Fourier transforms look like? So this is basically the conjugate symmetry. And then in part, this is more, they have this book. In this book, they have dealt with little more in deep. What happens is the real part of x and imaginary part of x of omega. Mark, see, this is what we told just above, that if x of t is real, then the magnetic spectrum will have even symmetry, but the phase spectrum will have odd symmetry. All these things we told. You can read this book or this chapter or this table in the book for more details. Okay, and one thing I would like to note, what is called the duality property of Fourier transform. Very useful property. What it says is very simple. If small x of t is the Fourier transform of small x of t has the Fourier transform capital X of omega, then suppose if I were to consider a time domain signal whose function is of the form capital X of t, then its corresponding Fourier transform will be 2 pi times x of minus omega. Small x. You see, if small x has a Fourier transform capital X, then the capital X signal, when you think about it in the time domain, will have the Fourier transform 2 pi times the small x of minus omega. That is, you just do a frequency reversal, but you take the same small x of t, which you consider in the first step. This is called duality property. That is, if you take the time domain signal as x of t, and then Fourier transform is, let's say, y of f, then if I were to consider the time domain signal as y of t, then its corresponding Fourier transform will be x of minus f times 2 pi. That's what this is saying. It's called duality property. Okay, very useful property. This also I will illustrate using an example today. Finally, we have the famous Parseval's relation for aperiodic signals, which says that you integrate x of t square in the time domain and you integrate x of j omega square in the frequency domain. They both will be equal. What this says is that the energy of a signal remains same in both time and frequency domain. It doesn't change. Basically, law of conservation of energy, right? You basically just represent the same signal in different domain. That will not increase or decrease energy. This is called the Parseval's relation of Fourier transforms. Now, I have also given some Fourier transforms of some common signals here. I will skip this today, but you can, anyways, these notes are made available to you. You can go through in your free time. Okay, all these things are very similar to Laplace transform only. Okay, so for example, delta of t also had the Laplace transform 1. Delta of t minus t naught has a Laplace transform e power minus s t naught. But now put s is equal to j omega, you get this number. Like that, you can just go through on your own. Okay, now I will give you an example of how does x of 80 look like, because I don't remember whether we did this in the previous classes. So let's say x of t is a signal like this. Okay, it's a rectangle signal between -1 and 1, taking the amplitude 2, and from here, from minus infinity to 1, it takes a value 0. From 1 to infinity, it takes a value 0. So this is a rectangle signal. It's a finite duration rectangle signal in the time domain. Now suppose I choose a number a, which is equal to 2, fine, and 2 is greater than 1. And if I want to plot x of 2t, then how does it look like? So basically how to plot x of 2t is, what you should do is, you should first write down whatever is the actual signal. So actual signal is what, x of t, and that takes a value 2 if t lies between -1 and 1, and it takes a value 0 in any other interval. Right. Now basically on the same token, what it says is whatever is the argument in x of t, that argument, when it takes a value between -1 and 1, you get the value 2. Else it takes a value 0. So that means x of 2t should be taking the value 2 if 2t lies between minus 1 and 1, and it takes the value 0 and otherwise. That means what? So 2t is between minus 1 and 1, or t is between minus half and half. Just divide by 2 on both sides, right? That means it takes the value 2 if t lies between minus half and plus half, and takes the value 0. If I plot this, what happens? It's the same signal as above, but it is now between minus half and half. Earlier it was, the amplitude is same. Earlier it was between minus 1 and 1, but now it has become minus half and half. Basically what happened? It got compressed. Got compressed from minus 1 to 1 to minus half to plus half. It's called compression of signal. And when does it happen? When you plot x of at for a greater than 1. If I had chosen a is equal to half, let's say, which is a number less than 1, then what would have happened is x of half t. Then what would happen? Instead of 2t, I would have got t by 2 between minus 1 and 1, or t between minus 2 and 2. So instead of having this, I would have had something like this. I would have from minus 2 to 2, I would have the amplitude 2. This is x of t by 2. Correct? So now this is what? This is called expansion. So whenever you time scale a signal x of t with a number a greater than 1, you will have a compression. And when you time scale a signal x of t using a number a less than 1, you will have less than 1, you'll have expansion. Greater than 1, you'll have compression. Is this clear? Can anyone confirm if what we discussed just now is clear? The example is clear?
Yes, sir.
Okay, great. This is about time scaling. Okay. Now coming to duality. It's a very, very useful property. You are often very handy in all your exams like gate exams or even your semester exams. Very, very useful property to know. So this is how the illustration goes. So let's say your x of t is a rectangle signal, right? It begins between minus 1 and 1, taking the value, the amplitude 2, and it takes a value 0 everywhere else. Okay. Now, if I compute its Fourier transform, you can show that for a rectangle signal, the Fourier transform turns out to be sinc signal. I mean, can you tell me what is a sinc function? Can anyone tell me what is sinc? What is a sinc x? What does it mean?
Sin x
Hello.
by x.
Yeah, that's right. But we will not take the definition sin x by x. We will take the sin x by x is basically what mathematics people say. But for signal systems course, what we will adopt is we'll adopt a slightly different definition. We'll say it is sine of pi x by pi x. Okay, this is basically the definition we will adopt in the generally it's adopted in the engineering field, at least in our electrical engineering field. Sinc x is defined as sine pi x divided by pi x. Okay, so what you can show is that you can just do the integration. Basically what I'm saying is you do x of t e power minus j 2 pi or omega e power minus j omega t dt from minus infinity to plus infinity with x of t given by rectangle signal. You can show that this will come out to be sinc function of omega. Okay, that is the Fourier transform will exhibit a sinc nature. Okay, now what I will do is just for illustration, I will call the Fourier transform as C1 times sinc of C2 omega, where C1 and C2 are some constants that depend on the duration of your rectangle and the amplitude of your rectangle. Okay, depending on what, so if it is minus 2 to plus 2 with amplitude 3, this C1 and C2 will accordingly vary. But the nature of the function, namely to the sinc, will not be different. For any rectangle signal time domain, its frequency Fourier transform will be a sinc function, but with different parameters. C1 and C2 can depend on the actual values of the time domain signal you take. Okay, so this is what you know already. Okay, so that small x of t, if I compute the Fourier transform, I'll get capital X of omega sinc function. Now suppose if my time domain signal itself is sinc of t. Okay, let's say consider some function y of t which is equal to sinc of t. So this is basically the sinc function. Then what happens is that in the integral you need to put sinc of t into e power minus j omega t, and in turn this will have sine pi a pi t by pi t into e power minus j omega t. It's a very complicated integration to perform. See, you have three functions of time coming all together in different complicated ways. It's not a very easy function to integrate. So we will use the duality property. What it says is simple. I know that already that rectangle signal gave rise to sinc function in the Fourier domain. So if I consider sinc function in the time domain, it is nothing but 2 pi times x of minus omega. That is, it is basically the you take the actual x of t which gave rise to sinc function in the Fourier domain. You do a time reverse. I mean, the not time reverse, frequency reverse. It's minus omega, not minus t. Okay, and then multiply by 2 pi. That's what this frequency duality property says. So a sinc signal will have the Fourier transform, a rectangle signal, but with flipped frequency reversed. That is, but it's a rectangle signal, it's even functions. It doesn't matter whether you reverse it or not. It will still look the same. So basically, your y of omega is equal to x of t. So this is basically the duality property. So this also says one important thing, that rectangle signal will have sinc function as a Fourier transform. Similarly, a sinc function will have the rectangle signal as a Fourier transform. Is it clear? This is basically the duality property. Is it clear? Hello? If it's not clear, you can just ask me. I can explain again. Okay, I see one student saying yes. So I guess it's okay. But you can ask me and stop me anytime and ask me. I can explain again. I can explain a little more detail also. Okay, you can stop me anytime and ask. Okay. The next is frequency response of a system. What it says is simple. If you take x of t as an input to a signal whose impulse response is h of t, and let's say I get y of t as output. Now, if I take the Fourier transforms of each of these signals, x of t, impulse response h of t, and output y of t, then they are related by the multiplication property of their Fourier transform, that is x of omega times h of omega is equal to y of omega, or h of omega is equal to the ratio of the output Fourier transform to the input Fourier transform. Now, this h of omega is what is called the frequency response of a LTI system. Why LTI? Because this product itself came about only because time domain you had convolution. Convolution is only convolution will only be will only be characterizing the output of an LTI system, not for any system. So for an LTI system, you can define the frequency response as the ratio of the output Fourier transform to the input Fourier transform. Okay, so if it were Laplace transform, then it is called transfer function. If you take the Fourier transform, it's called the frequency response. And now it turns out that if I pass a signal x of t is equal to e power j omega naught t, you will get an output which is a scaled version of e power j omega naught t. So that's why this is called eigenfunction. So basically what I'm saying is, if x of t is this, then what happens is y of t, you can show that this turned out to be some lambda times e power j omega naught t. You can show that this is a property of an LTI system. Okay, so this is basically, since this output is a scaled version of the input, this function, the function is called eigenfunction. Why eigenfunction? If you have done some elementary, high school, I mean, or even first semester or second semester linear algebra course, there is a concept called eigenvalues and eigenvectors of a matrix, right? So if a matrix A has said to have an eigenvector x and eigenvalue lambda, if it satisfies Ax is equal to lambda x. So what basically it says is that if I take the vector x, I operate it with the matrix A, I get back the same vector x but scaled by some lambda. That is basically the meaning of the expression Ax is equal to lambda x. That is what is happening here also. You give the input e power j omega naught t, the output is scaled version of e power j omega naught t. And here, if you go back to Ax equal to lambda x, so such a x was called eigenvector, right? So similarly here, such a function is called eigenfunction. And here the lambda value is called eigenvalue, and similarly here also is called this is also called the eigenvalue of the system. Okay, so that's basically just a small note in where is it used. Very useful very useful for practical applications. Wherever we want to So let's say we are given a system and we don't know what is the characteristic of system. We don't know the impulse response. We don't know the frequency response. They will use this eigen. What they will do is they will pass an eigen function as the input, and they will take the output. And they already know that eigen function has a property that the output will be scaled version of input. So all they will do is they will divide output by input. What will remain is lambda, and this lambda will correspond to the Fourier frequency response of the system. So like that, they will do for different omega naughts, right? So omega naught is one frequency. So pass, let's say, e power j omega 1t, you will get output lambda 1 into e power j omega 1t. You pass e power j omega 2t, the output will be lambda 2 into e power j omega 2t. Like that, you keep passing for different omegas. You will get lambda 1, lambda 2, and keep on, you will accumulate all those values. So now you have found the frequency response of the system. Now you do inverse Fourier transform, you got the impulse response of the system. So this is basically what is called system identification problem. It's called system identification. You are identifying what kind of system is this, the properties of system. So eigenfunctions are very useful in that kind of a application. These are little advanced uses of advanced signal processing techniques. But for the purpose of this course, just know what an eigenfunction is. That is, output is a scaled version of input. Okay, distortionless transmission by a system. What it says is that if your output is basically scaled and time shifted version only. If I pass x of t as the input, but the output can only be a scaled and time shifted version. It should not be any other version. Only time shifting and scaling is allowed. Only these are allowed. If a system can do only that, it won't do anything else. Then basically such kind of a system will produce a distortionless response. Okay. So for example, for such a kind of system, it should have two properties. If you look at the magnitude spectrum, it should be constant. It should be a constant as a function of omega. And the phase spectrum should be linear. It should be a linear function. So if these two conditions are satisfied by a system, then that system will produce an output that is following this way. That is, it will produce a k times x of t minus t naught, or a distortionless response. It will allow it only do time shifting, and it will only do some constant multiplication. It will not do any other operation. Okay, why are these useful? Again, if you take a follow-up course on what is called on the digital signal processing and or discrete time signal processing or any other signal processing courses, you will end up with something called FIR filters, IR filters. There are so many more advanced signal processing, blocks that you want to construct for some practical application. There, if I want to construct a particular, let's say, a filter, then I should be knowing what are the properties that this filter will exhibit. I don't want a distorted response of the system. The output should be distortionless response of what is the actual input, right? So that means I need to design my system so that these conditions are satisfied. For this, I need to know the properties, namely that you should have a constant magnitude response, you should have a linear phase response. If I know these properties, then I can accordingly design a system so that the output of some desired application will be a distortionless version of the input. Okay, these are, for now they are like facts, but as you keep going on throughout the semesters, you will appreciate okay. Next is basically filters called ideal filter. Basically, what is a filter? Filter is basically a system. It's basically a system which allows only certain frequencies to pass through it. For example, a low pass filter is one where the frequency response is something like a rectangle signal only. It has a amplitude of 1 from minus omega c to plus omega c, and it has a 0 everywhere. So if you remember, then what happens is that if you pass the input x of omega, it will get multiplied with h of omega, right? Therefore, since outside of this h of omega, outside of this minus omega c to plus omega naught c, h of omega takes the value 0. Any component of x of omega outside of minus omega c to plus omega c will be equal to 0. That's why it basically rejects, or the output will not contain any frequency components outside this range. That is from minus infinity to minus omega c, and omega c to plus infinity. It will not contain any signal, any component in the output. That's why this filter is also called low pass filter. It will only pass low frequency components from the input to the output. So if you look at the frequency response of a low pass filter, it looks like this. So this omega c is called the cutoff frequency. That is beyond omega c, no, it will not pass any other frequency, and before omega c, it will pass everything else as is because it is just multiplying by 1. And high pass filter is the complementary. That is, it will not pass any frequency in the lower dimension, in the lower frequency, but it will pass any frequency which is more than omega c or less than minus omega c. Okay, anything around 0, nothing it will pass. Band pass. Band pass filter is basically one which will pass only a selected range of frequency. Let's say from omega 1 to omega 2. It only pass this much. It will not pass any other frequency components to the output. Okay, the frequency response of a band pass filter will look like this. Similarly, what is called a band stop filter, right? Band stop filter means it's also called notch filter. That is, it will selectively not allow only a particular frequency band to pass. So let's say you see omega 1 to omega 2, the frequency response is 0, but everywhere else it is 1. Similarly, from minus omega 2 to minus omega 1, the frequency response is 0. That means the output will not contain any frequency components from omega 1 to omega 2, but it will contain the frequency components at any other frequency. This is called a band stop filter. You will design these filters very more sophisticated versions are there, like Butterworth and Chebyshev filters. All of them are dealt in DSP course, digital signal processing. Okay, and finally we'll end with, okay, a practical filter, you cannot realize it like this. Okay, you cannot have a sharp transition. What generally happens is you allow for some gradual transition. Okay, let's say from omega c, it will not have a sharp one, but the actual realizable filter will be such that its frequency response will still have some non-zero number outside omega c, but it will go to 0 eventually. So let's say omega dash is where it goes to 0. This is like a transition band from omega c to omega dash. So strictly it is low pass between minus omega dash to omega dash, not minus omega c to omega c. Okay, this is called the transition band. Fine. So that was about, I think it did take a little bit time, but it's okay. We also saw examples of time scaling and duality property. So are there any doubts?
No, sir.
Okay, thanks. So let's start with some problem session. So I remember last time we did not solve many questions in Fourier series. We just did some Z transform questions, and then we started with Fourier series. We saw Euler's expansion of Fourier series. How can you use Euler's expansion to compute the Fourier series? And we did one problem on square wave, right? We took a rectangle signal or a square signal, and then we found the Fourier series. So the first part, what I've done is I'm going to quickly recall that problem, and I'm going to solve some series of problems built on this problem. I'm going to consider different varieties of square signal. I'm going to compare how the values of Fourier series for those signals are compared to the Fourier series of this signal. Okay, so let's just quickly go through. So the question, this is basically the same question which we did last class. So let's say you consider the periodic square wave as shown here. So it has a value a from 0 to t naught by 2, and the value 0 from t naught by 2 to t naught, and then it repeats like this in for every other, it keeps repeating for every t naught. So t naught here is called the fundamental period, and note that it's an odd signal. Why? Because if you compute x of minus t is equal to minus x of t. Okay, so this is not a even signal. So the question then was, what is the complex exponential Fourier series of this x of t? Second question is, what is the trigonometric Fourier series of x of t? So let's quickly go through how did we solve. We first noted that your x of t, the Fourier series given by minus infinity to plus infinity ck e power j k omega naught t, where omega naught is the angular frequency given by 2 pi by t naught, where t naught is the fundamental time period. It's given in the question already. So assume that t naught is the fundamental time period. Now, how to compute ck? We computed ck by the integration 1 by t naught integral 0 to t naught x of t e power minus j k omega naught t dt. And so basically, what did we say? X of t takes a value a from 0 to t naught by 2, and it takes a value 0 from t naught by 2 to t naught, right? And that's what we did here. Okay, so in the range t naught by 2 to t naught, the x of t is 0, so there is no integral. So this is as good as saying ck is equal to 1 by t naught integral 0 to t naught by 2 a into e power minus jk omega naught t dt. A is a constant, we took it out. So a by t naught, 0 to t naught by 2, e power minus jk omega naught t dt. And we just took this like e power x integral over x, right? Dx. It's like that form. There is nothing but just e power x. But if there's a cx, then e power x, e power cx by c is the integration formula. And that's what we did here. And then apply the limits from 0 to t naught by 2. And then we just simplified a bit. And then we got this as the answer. Okay. And we also told that omega naught is equal to 2 pi by t naught. So omega naught t naught is equal to 2 pi. So what did we get? We got this expression. This is what we did last time. Okay. So whenever k is not equal to 0, and for k even k, we got ck is equal to 0 because minus 1 power even is 1. So 1 minus 1 goes to 0. Whenever k is odd, then minus 1 power k is equal to minus 1. In which case this whole will become 2. So you'll get a by j k pi. That's what is this ck. And when k was equal to 0, you cannot apply this definition of, you cannot directly find ck from here because it will give 0 by 0 form. So go back to the definition of ck, this integral, put k equal to 0 here. So that means this goes away. So you get this expression. So this is nothing but the area under the curve, right? Area under the curve x of t over one time period. And this comes out to be a naught by 2. So what we saw is we summarized that c naught is equal to a by 2, c2m for any 2m means for even k is equal to 0, and for odd k it is a by j2m plus 1 into pi. So the Fourier series is x of t equal to c naught a by 2 plus a by j pi summation m equal to minus infinity to plus infinity 1 by 2m plus 1 e power j2m plus 1 omega naught t, where omega naught is equal to 2 pi by t naught. This is what we did in the last class. Okay, so now we will consider different signal, slightly different signal. Okay, consider signal x of t, which is basically shifted to left by t naught by 4. So you see this, now this has become even signal. So you see, go back to this signal, first signal. It was starting, the rising edge was at 0. I have slightly shifted the rising edge to left. Okay, this was an odd signal. You see, this has an odd symmetry. But if you look at this signal, I have slightly shifted the rising edge by an amount of this t naught by 4. Okay. This is based. Now, if you look at this signal, it's an even signal. Now, my question is, what is the Fourier series? Yeah. Find the complex and trigonometric Fourier series of x of t. Okay. We'll solve it. What will happen? Let's do it. So again, same thing. There's no, we're going to do the same thing, but we are going to do more carefully and interpret why the answers are different. X of t is a Fourier series, summation over ck e power jk omega naught, where omega naught is 2 pi by t naught. Okay. And now basically where ck is given by 1 by t naught. Now, the way I will do this is, I will not consider 0 to t naught. I will consider minus t naught by 2 to plus t naught by 2, because my Fourier series definition says I should do over one time period. It doesn't say that it should be only between 0 to t naught. Over one time period, I need to integrate. I need to integrate to compute ck. Why I'm doing minus t naught by 2 to plus t naught by 2? Because this is one nice, function. This is like this. Now you can think of this block to be repeating in every t naught, right? Okay, that is, it is 0 between minus t naught by 2 to minus t naught by 4. Then it is a between minus t naught by 4 to plus t naught by 4. And again goes 0 between t naught by 4 to t naught by 2. Just that it has some nice symmetrical structure. If we use that, our integration will become easier. Okay, that's it. Now I will choose the interval minus t naught by 2 to plus t naught by 2. Okay, and that's what I'm writing here. And you can decompose this as what I just said told. Minus t naught by 2 to plus t naught by 4. You see this signal. So minus t naught by 2 to plus t naught by 4, the signal value is 0. Therefore, I put 0 and the entire integration goes 0. The second signal is minus t naught by 4 to plus t naught by 4, in which case it takes the value a. So I just put a. Third range is plus t naught by 4 to plus t naught by 2. Again, it takes a value, so value 0. So again, the third integral will go to 0. So what remains is only the second integral, and a is a constant, take it out. So it is a by t naught into integral minus t naught by 4 to plus t naught by 4 e power jk omega naught t dt. Okay, this is a definition of ck. Now do the integration. This is nothing but a by t naught into e power minus jk omega naught t divided by minus jk omega naught, limit from minus t naught by 4 to plus t naught by 4. This is nothing but this number. I just subtracted these two numbers. Fine, and I got equation 1. Okay, now I know that omega naught is equal to 2 pi by t naught. So omega naught t naught equal to 2 pi. So just put that here. So you have omega naught t naught, put 2 pi, omega naught t naught, put 2 pi, omega naught t naught, you put 2 pi. So all these three places you put 2 pi, you get this expression. Now see what this is left, the form a by jk 2 pi e power jk pi by 2 minus e power minus jk pi by 2. You take 2j from here to inside. Okay, now can anyone tell me what is this number here? E power jk pi by 2 minus e power minus jk pi by 2 by 2j.
Sine function.
Exactly, that's the Euler's expansion of sine. Okay, this is nothing but sine k pi by 2. Right, so this is basically the Fourier, the coefficient ck. Now again, this is not applicable for k equal to 0 because again it gives sine 0 by 0, which is 0 by 0 form. So you should not use this formula for k equal to 0. You should again go back to the definition of ck, but we'll come to that. Let's say k is not equal to 0. Okay, then for even k, let's say k equal to 2m. Okay, that is an even number. Then basically ck is same as c2m, which is equal to a by 2m pi into sine 2m pi by 2. But 2 cancels, so sine m pi. But sine m pi is equal to 0 for any m being an integer, right? So what it says is that all even Fourier coefficients will take the value 0. But if the Fourier coefficient is odd, then let's say k equal to 2m plus 1, where m is some integer, then ck is c2m plus 1 equal to a by 2m plus 1 into pi times sine of 2m plus 1 pi by 2. And now this you can again write it as this inside sine, you can expand it as 2m pi by 2 plus pi by 2. But these are the form sine pi by 2 plus theta. Sine pi by 2 plus theta equal to cos theta. This is a well-known trigonometric formula. Okay, I'm just using that expression here. So this is a pi by 2 and this is like theta. So this becomes cos 2m pi by 2. 2 get cancelled, so it becomes cos m pi. But I know that depending on what m is, so if for example if m is equal to even, then cos pi will be equal to 1. Sorry, cos m will be equal to 1. M pi will be equal to 1. If m is odd, let's say, sorry, m is equal to even will be 1. If m is odd, then cos m pi will be equal to minus 1. So you can write both cos m pi is nothing but minus 1 power m. Okay, and a by 2m plus 1 into pi carries forward everywhere. So this is my expression for the Fourier coefficient when the k is odd number. Now at 0, go back to the definition, that is c naught is equal to, you can do over any interval. You can show that it doesn't, you can again do this from minus t naught by 2 to plus t naught by 2. Anything is okay. Here anything is okay because I don't have that e power minus j to j omega naught t coming. Just to simplify the integration, I chose a different interval. But here it doesn't matter because x of t, it doesn't matter whichever interval you choose, as long as it is over one time period. So the c naught will be, you can show that this integral will come out to be a by 2. Therefore, if you substitute for all these values, you get x of t is equal to a by 2 plus this basically c naught, and you only have contributions from even k, right? That is from 2m, sorry, odd case, not even case. So basically, you will have 2m plus 1 coming up and 2m plus 1 j. Basically, if you look at this, what is this? A by 2m plus 1 into pi. That's what I wrote. I just took a by pi outside, but 2m plus 1 you should not take out because the summation is over all m. Okay, minus 1 power m because of this minus 1 power m. And omega naught is equal to 2 pi by t naught. So this is the complex exponential Fourier series. Now, how will I compute the trigonometric Fourier series? Recall that for the we did this in the last time. That is, if we are given trigonometric Fourier series coefficients, we can find out complex exponential series Fourier coefficients. Similarly, if we are given complex exponential Fourier series coefficients, you can also find trigonometry expressions. That's what I'm going to do here. So basically, we know that a naught by 2 is equal to c naught, but c naught we computed to be a by 2. Therefore, a naught is equal to a. For a real signal, you see this is real signal, right? Square signal only. It takes only two values, a or 0. Both are real numbers. So this is a real signal. So for a real signal, you have this relation satisfying. That is a to m is 2 times real part of c to m, and b to m is 2 times minus 2 times imaginary part of c to m. Okay, where a and b are the coefficients of cos and sine series in your trigonometric Fourier series. And you see that a to m will come out to be 0 because c to m's are 0. We saw that, right? So you see c to m's are 0 here. C to m's are 0. Similarly, a to m plus 1 will have some number. Similarly, b to m will be a function of c to m is also 0. But b to m plus 1 will also be 0 because although c to m plus 1 is not 0, imagine, see, c to m plus 1 is a real number. See this number? This is a real number. It's not a complex number. So real part of this is the same as this. The imaginary part of this is equal to 0. That's why b to m plus 1 also became 0. Or if both even and odd values of b are 0, or for any value of k, bk is equal to 0. Now, therefore, basically, what we just recall the trigonometric Fourier series looks like this: x of t is equal to a naught by 2 plus sum over k equal to 1 to infinity ak cos k omega naught t plus sum k equal to 1 to infinity bk sin k omega naught t. Now, third term will fully go 0 because bk is equal to 0 whether k is odd or even, doesn't matter. But for ak, what did we see? For whenever that k is even, this is 0. Whenever it is odd, it takes this number. Therefore, we retained only 2m plus 1 terms. Okay. Now, basically, this is what is the trigonometric Fourier series expansion of the squares, the signal that we saw. Okay. Now, basically, you see this. This has only cos terms. But if you recall, go back to the notes. So basically, the trigonometric Fourier series has only cos terms here. It doesn't have any sine terms. But if you go back to the notes of previous class, this signal, what we did in last class, right? This the rising edge odd, the so-called odd signal. This had only sine terms but not cos terms. Can anyone tell me why did this difference come? We just shifted it by a small amount. The entire Fourier series got changed. Can anyone tell me why only sine terms will exist for this signal, but only cos terms will exist for the slightly shifted signal? Yes? Okay, I will tell the answer. Simple. This is not an even signal, it's an odd signal. Recall that an odd signal, a cos term, a cos t is not an odd signal. It's an even signal. Right. So if it's an even signal, it cannot contain, if it's an odd signal, it cannot contain even components, signal components. That's why, but sine signal on the other hand was an odd signal. Right. Do you understand? Sine x, sorry, sine t, let's say sine t is a odd signal. But cos t is an even signal. Now, this signal is an odd signal, right? This signal is an odd signal. Therefore, even in the Fourier series representation, this cannot contain an even signal. It can only contain odd signal. That's why it had only sine t terms. It didn't have cos t. But on the other hand, if you go back to this signal, it's an even signal. It's not an odd signal. Therefore, for an even signal, it will only contain cos terms, which are even signal terms, and not the sine terms, which are odd signal terms. If your signal was neither odd nor even, that is, nothing was whole, then you will have both sine and cos terms in the trigonometric Fourier series. These are basically high level, verification whether our answer is correct or not. Suppose if you have gotten sine terms here, but the actual signal is an even signal, then there is something wrong in our calculation. That answer is not correct. Okay, these are some simple tricks to verify whether our answer could be correct or not. But of course, these exact numbers we cannot verify whether, let's say, is this a correct coefficient or not. We cannot verify if it. I mean, you just have to go through the steps. You should just make sure the steps are correct. Then this is correct. Is this clear? Why this has cost but not sign, but the first one had sign but not the cost? Is this clear?
Yes, sir.
Yeah. Okay, I think we are at 7:04. It's 7:04 p.m. now. We can take a quick break, maybe till 7. We can take a break till 7:20, and then we can come back and then solve the rest of the problems. You can be online. You don't need to uh, leave the meeting. You can be online, but you can just relax. Yeah, I think one of you have joined. We are actually under break now. We'll actually resume with the questions in another 10 minutes. So you can be online only. No need to exit the meeting. Okay. Um, let's begin. Are you able to hear me?
Yes, sir.
Okay. Thanks. Okay. So now we will consider another square wave. Can you tell me the difference? What is the difference in this third question than the first two questions? The only difference is that we had either 0 or a, but now we are allowing the 0 to go till minus a. In the first two questions, it was only going from 0, either it was 0 or a, but now we are allowing this to go from minus a to plus a. That's the main difference. And let's see, what I will now do is I will illustrate how to find the answer to this question without really computing the integral for the Fourier series transform coefficients, without really computing that integral, just by using the properties of Fourier transform. Sorry, not transform, series. We are still doing series. We'll do a good number of problems on transforms subsequently. So the question is, okay, this is the periodic square wave. The question is, find the complex exponential and trigonometric Fourier series of x of t. So what I'm going to do is I'm going to consider this signal, another signal x1 of t, which is given by a signal which is taking the value 0 between minus t naught by 2 to plus 0. And it takes the value 2a, not a, but it takes the value 2a from 0 to t naught by 2, and again takes the value 0 from t naught by 2 to t naught. So let's say this is the one time period. So in one time period, so the description is that the signal takes a value 2a from 0 to t naught by 2 and 0 from t naught by 2 to t naught. Okay. So see, the only difference, go back to the first question, recall the first question, how was it? The first question we had ta from 0 to t naught by 2 and 0 from t naught by 2 to t naught. But now instead of a, we'll have 2a. So let me call that as some signal x1 of t. So this is called x1 of t. And now I'll define another signal y of t as x1 of t minus a. That is, what I do is I will just shift the amplitude of the entire signal x1 I subtract the amplitude by minus a. So basically there are only two possible amplitude for x1 of t. It is either 2a or it is 0. Now if you subtract a, then all 2a will become, so 2a minus a is equal to a, and 0 minus a will become minus a. So all parts of 2a will now go to a, and all that part of signal in 0 will go to minus a. So you will get this signal. Okay, so from 0 to t naught by 2 you will have a, and from t naught by 2 to t naught you will have minus a. Okay, but now you see, this is exactly the signal that is there in the question. I'm just zooming out a lot. This is a question on the topmost. Question is to find Fourier series for this guy, and what it says is from 0 to t naught by 2 to you have a, and from t naught by 2 to t naught you have minus a, and that is exactly this y of t signal also. Correct. So what it says is that if I consider the signal x1 of t and I subtract it with a, I will get back the signal in the asked question. But what is this signal x1 of t? It's the same signal what we computed in the first question, but with a replaced by 2a. That means we are going to essentially use a linearity property of Fourier transform to solve this question very easily. We know the Fourier series of this signal already. We'll apply linearity property and get the Fourier series of this signal. That's all. Nothing else. Okay, that's what I'm going to do. So what I'm saying is this y of t is actually the x of t that is given in the question. Therefore, what I will do is that x of t, the given question, whatever is given in the question is nothing but x1 of t minus a. Removing, maybe I'll remove the arrow mark. I'll remove now. Okay, so x of t is equal to x1 of t minus a, where x of t is a question, the given signal in the question, and x1 of t is a signal that we constructed, where it is 2a from 0 to t naught by 2 and 0 from t naught by 2 to t naught. Okay, therefore, what does the linearity property say? The Fourier series of x of t is equal to Fourier series of x1 of t minus some constant a. That's all. Correct. Now, so basically, first is what I need to find the Fourier series of x1 of t. But I already have that in my hand, right? But for when the amplitude is a, but now it is 2a. So all I need to do is go back to the question for the first question, right? So wherever I have a, I replace it with 2a. Okay, so then what this first term will become a by 2 into 2a by 2 is nothing but a, and this will become 2a by j pi. Fine, and that's what I'm writing it here. A, okay, again I will now erase the arrow mark. A plus 2a by j pi into same thing whatever I wrote in the first, the answer to the first question. But now it is not just this, you need to subtract a from it, because that's the equation 1 says that x of t you can get when you subtract x1 or a from x1 of t. That's why now this a and this a will cancel out. That's what I wrote that time. This a and this a will cancel out. So basically all I will get is that x of t is equal to 2a by j pi into summation m equal to minus infinity to plus infinity 1 by 2m plus 1 into e power 2m plus 1 into j. I think there should be a minus, right? Let's go back to the question. First question. Okay. Here there should not be any minus, because if you look at the definition of Fourier transform, x of t is summation over e power plus jk omega naught t, not minus. Only in the integral for ck you will have a minus, but the actual definition of Fourier series will have e power plus j. So it is this. Okay. So you did not do we didn't do any calculation of Fourier series at all. What we did two things. We basically took the Fourier series of some other known signal, and then we applied the properties of the Fourier series, namely the linearity property, and then we obtained the Fourier series of this signal. Okay, and similarly, you remember for that signal we had sine terms on all those things we told, right? Now just there the same expression for trigonometric Fourier series, replace a by 2a, and then you subtract it minus a in the end. Whatever you get, that is the answer here. Okay. Is it clear? Is this technique clear? Can anyone confirm? Hello? Can anyone
Yes.
confirm if okay, it's
Yes,
clear?
sir.
Sure,
Yes, sir.
sure.
Please.
Yeah. Okay, great. So we are going to solve another question where again I'm going to use the properties of Fourier series. Okay, again interesting question, but you should very carefully listen. Then it will be very. It's actually very easy question. Again, we are not going to compute the Fourier series explicitly. We are going to take the Fourier series of a known signal and apply properties on it, and we'll get the Fourier series of the required signal here. So the question goes as follows: consider the triangle wave signal. So until now we dealt with rectangle periodic signals, but now we have a triangle periodic signal. It will keep on going. Okay, such that it has a linearly increasing ramp from 0 to t naught by 2. It increases till a, and then from a it decreases and goes to t naught. It goes to 0 at t naught. Again it increases to a from t naught to 3 t naught by 2. Again it decreases from a to 0 from t naught by 2 to 2 t naught. It keeps on repeating on both left and right side. Question is straightforward. Find the complex exponential Fourier series of the signal x of t and trigonometric Fourier series of the expression of the signal x of t. Okay, the first thing that we need to do is, what I will do is, okay, what I want to do is that I want to first write down like in the mathematically what is this function value. So this is basically a figure that plots the actual x of t. But mathematically, how can I write x of t in the form of a function, right? So for that, what I need to know is I need to know the equation of this line, and I need to know the equation of this line. If I know these equations, then basically I have characterized the entire signal in one time period. And every time period, the same line only will keep getting repeated, but by a shift. That's okay. Okay, so now basically it's some coordinate geometry, nothing else. So this is basically your 0 comma 0 origin, and this topmost, this curve, the black what I'm marking, has a coordinate t naught by 2 comma a. So then you can find the equation of this line. Simple. This is like y is equal to mx, right? Because it is passing through the origin. And so all you need to do is, what is the value of m? That is the slope. Slope is nothing but a minus 0, y2 minus y1 divided by x2 minus x1. So let's say that your this is your x2 and y2, and this is your x1 and y1. So basically what happens is y2 minus y1, a by 0, a minus 0 divided by x2 minus x1, t0 by 2 minus 0, which is nothing but 2a by t0. So 2a by t0 is the slope of the line. Therefore, in the region 0 to t0 by 2, your x of t is equal to 2a by t0 into small t. That's what I wrote in this expression here. When t lies between 0 and t0 by 2, your x of t is equal to 2 by t0 into at. Okay, so your t is your x-axis and x of t is like a y-axis. Now we need to find the equation of line in this region. Okay, I've just written it down here. So now what I will do is for this region, what is what is the coordinate is t0 by 2 comma a, and the second coordinate is t0 comma 0. Fine. So basically, what is the equation of when you have two coordinates? The equation is given by y minus y1 is equal to y2 minus y1 by x2 minus x1 into x minus x1. This is a parameter. I think this is one parametric form or something, right? Y minus y1 equal to y2 minus y1 by x2 minus x1 into x minus x1. This is the equation of a line if you're given the the coordinates of the two extreme points, two endpoints, right? So basically, that's what I'm applying. For this again, I consider that t0 comma 0 is x1 comma y1, and t0 by 2 comma a is x2 comma y2. Therefore, y minus y1 or y minus 0 equal to y2 minus y1 a minus 0 divided by x2 minus x1 t0 by 2 minus t0 into x minus x1 t minus x1 is t0. So here x plays the role of t and y plays the role of x of t. Remember that. So now just simplify this. You can show that t0 by 2 minus t0 is equal to minus t0 by 2. Okay, so that becomes 2a by t0, and that minus I will make it as here. Instead of t minus t0 becomes t0 minus t. Okay, but this y is nothing but x of t. Therefore, in the region from t is equal to t0 by 2 to plus t0, your equation, the signal value is 2a by t0 into t0 minus t. Is it clear till now? Is x of t clear?
Yes, sir.
Okay. Now what I will do, I will consider x dash of t, which is defined as the derivative of x of t. That is, you differentiate x of t with respect to t. Then what happens? X dash of t is nothing but d by dt of x of t. So 2a by t0 into t, if you differentiate, you get 2a by t0 between t between for t between 0 and t0 by 2. And for the for t between t0 by 2 to t0, if you differentiate x of t, we will get minus 2a by t0 because this t0 is a constant. So first term will go to 0 in the differentiation. So what is x? So what is x dash of t looking like? It is looking like when t lies between 0 to t0 by 2, it is taking 2a by t0. When t is lying between t0 by 2 to t0, it is taking the value minus 2a by t0. And similarly, this keeps on repeating, right? Because essentially, what is the differentiation? Derivative is the slope of the line, right? You see here, this line, this line, this line, and this line. All these rising edges all are parallel to each other, which means they have the same slopes. Therefore, if you take the derivatives in the respective time intervals wherever they are rising up, you will have 2a by t0 constant. Similarly, if you look at the curves, whichever is falling, right, from let's say t0 by 2 to t0, 3 t0 by 2 to 2 t0, and similarly the left hand side, right hand side, all these guys are now parallel. So they will have the same slope. Therefore, in these intervals, whenever they are falling back to 0, they will have the same value of slope equal to minus 2a by t0. Therefore, this is now what? So basically, this is a square wave, a periodic square wave. And now this is exactly the signal for whom we calculate the Fourier series in the previous question. Correct? You see the only difference is instead of with a different amplitude. Here we have 2a by t0, but you go back to the previous question. This was a question. Here we have just a, but exactly the same signal only comes except for the change in the amplitude. Therefore, simple. What should we do? If I want to find the Fourier series of the derivative, all I need to do is take the Fourier series expression from this question, replace a by 2a by t0. Is it clear? This will give you the Fourier series of the x dash of t. Is it clear?
Yes, sir.
Yeah, that's what I'm going to do next. Okay, therefore from the previous question, you replace a by 2a by t naught. Therefore, you get the complex exponential Fourier series of x dash of t, not x of t. Still x of t we need to come, because x of t is a triangle wave. We have only found the Fourier series of this square wave with amplitude 2a by t naught. Okay, so this is a complex exponential Fourier series of the square wave with amplitude 2a by t naught. All it is, just replace a by 2a by t naught in the previous question. Now, I need to find the Fourier series of actual x of t, right? So what I will do, let me write down the actual equation of Fourier series. What is the Fourier series of x of t is nothing but summation k equal to minus infinity to plus infinity ck e power jk omega naught t. And I need to find ck. That's the goal. I differentiate this equation with respect to t on both sides. Okay, so this becomes d by dt of x of t, which is equal to x dash of t only. The right hand side, the only place where t is coming is in the complex exponential term. Therefore, it becomes ck into jk omega naught into e power jk omega naught t, because e power cx, if you differentiate with respect to x, is nothing but c into e power cx by chain rule. Right? So the Wesco coefficient of t is jk omega naught. That's why it comes and multiplies the ck also. This is the difference. This is basically the differentiation of your x of t. Now, see, this is what is this? This is basically x dash of t, and this is actually what's called this as some dk. So dk into e power j k omega naught t. Now, is this not the Fourier series of x dash of t with Fourier coefficients dk? Is it correct?
Yes, sir.
Exactly. I'm going to do that. So what do I but I know the value of dk. Why? Because equation 1 I found already the Fourier series, right? I know the value of dk. So using dk, I will now compute ck. Ck is the Fourier coefficient of the actual signal x of t. That's what I'm going to do. Okay. So I'm going to compare equation 1 and 2. That is this x dash of t, which will have this dk into e power jk omega naught t, and the actual equation um, in the equation 2, which basically tells how is dk a function of ck. Okay, so let's say at k equal to, let me now just zoom out a bit. Now you see, whenever k is not equal to 0, right? So this contains only even k, right? Because it's a form 2m plus 1. We don't have any 2m coefficients. Therefore, whenever k is a even integer, your dk is equal to 0, or ck into jk omega naught is 0, or ck is also 0. But whenever k is an odd integer, what happens basically, what is basically the thing is, your dk is what? The coefficient 4a by j. um, uh, yeah, so basically you see 2m plus 1 is the value of k. So basically what you have is that 4a by jk pi t naught into, okay, one more 1 by k came, no? There are two k's. Not sure. Can you see that there are two k's? Why? I mean, I now don't remember. Why did I write k 2 times k? Because just 4a by j pi t naught into 1 by k. If 1 by 2m plus 1 is like 1 by k. So your dk should have been just 4a by j pi t naught into 1 by k. This is your dk. Is it okay? And now you equate that to dk, which is equal to ck into jk omega naught. Yeah, correct. You should not have one k here. It's only you should be only 1k. Fine. This is okay. Is it okay? I have removed 1k. So all I have is that my dk, which is equal to 1 by k into 4a by j pi t naught, is equal to ck into jk omega naught. Therefore, what I do is jk omega naught, bring it to the RHS. So ck is equal to minus, this minus is coming because j into j square is -1. Minus 4a by k square pi t naught into omega. K square is coming because there's a k here, there's also k here, so k square comes. Pi is already here. T naught is already here. Omega naught is coming from the LHS again. Okay. And now what we know is that omega naught T naught is equal to 2 pi. So this also becomes 2 pi into pi, that becomes 2 pi square. So that if it's 2 and 4, so it becomes 2a by pi square k square minus with the minus. And C naught is basically, you do C naught is not that difficult. Just do the integration of this basically the area under this rectangle in one period. Whatever the area under the, sorry, not rectangle, triangle. If you look at the area under this triangle, half into base is what? T naught into height a. So a T naught by 2. You need to divide by T naught also. So it becomes a by 2. Okay. So you collect C naught, and then you have collected the values for C for an odd integer, and for C for even integer is 0. Right? Ck is 0 if it's an even integer, and Ck is equal to minus 2a by pi square k square if k is an odd integer. Therefore, you collect both of them. So a by 2, which is C naught, and minus 2a by pi square into sum over 1 by 2m plus 1 the whole square into e power j 2m plus 1 omega naught. Similarly, what you do, you find out you take it as a homework. This one, we have the trigonometric Fourier series. Now try to relate the trigonometric Fourier series of this, differentiate, then try to take the trigonometric Fourier series of this and differentiate this and compare both the terms. Okay. And you can show that the trigonometric Fourier series will be of this form. Was the trick clear? Any doubts? Are there any doubts? You can unmute and answer. Or which part is not clear? Can anyone unmute and tell if it's clear or not clear or anything? Yes. None of you are responding, so I don't know whether it's clear or not. Anyone can respond and tell if it's clear or not clear. Anything is okay. I can explain again if things are not clear.
Sir, clear.
Yeah, which part you have doubt?
Sir, no doubt.
Oh, no doubt. Okay. Sure. Thanks. Okay. Then the next question is another periodic signal. So it's a periodic impulse train. So impulse trains means basically that you have an impulse function, and it is a period. You just repeat this impulse function with some period. Let's say here it's t naught. For every t naught, this impulse function keeps repeating. This is called an impulse train. Okay, and it's a periodic impulse train with period t naught. So that is basically here. That means this impulse at t is equal to 0 is delta of t. The impulse at t equal to t naught is delta of t minus t naught. Impulse at 2 t naught is delta of t minus t 2 t naught, but everywhere else is 0. So every impulse in its own right, it's 0 everywhere except for the argument whenever the argument is 0. For example, delta of t minus t naught, the argument is 0 when t is equal to t naught. That's where at t naught you have a 1, but everywhere else it's 0. Similarly, delta of t minus 2 t naught will have a 1 when t is equal to 2 t naught, and everywhere else it's 0. Okay, so fundamental period is t naught. So you can write this x of t compactly as x of t is equal to summation k equal to minus infinity to plus infinity delta of t minus kt naught. Okay, where k is the running integer and t naught is the fundamental period. Okay, you can show that if you plot this, it's exactly this. It's exactly this impulse train. Okay. Now the question is again straightforward. Find the complex exponential Fourier series and the trigonometric Fourier series. Okay, so yeah, this one, it's a little straightforward, not too difficult. So x of t, the expression for Fourier series is that summation k equal to minus infinity to plus infinity ck e power jk omega naught t, where omega naught is equal to 2 pi by t naught. Now, what is the value of ck is nothing but 1 by t naught into integral minus t naught by 2 to plus t naught by 2. That is, I'm just taking one interval. What I'll do is I'll just take this as my interval. So for every such interval, the signal is going to be the same. Namely that from minus t naught by 2 to t naught, you have 0. At t naught, you have an impulse. From minus t naught by 2 to 0, you have 0. At 0, you have an impulse. From t naught to 0 to t naught by 2, you have 0. So that's basically the one periodic, one periodic interval. Okay. So I'll consider from minus t naught by 2 to plus t naught by 2 x of t e power minus jk omega naught t dt. But x within the interval minus t naught by 2 to plus t naught by 2, I only have delta of t. I don't have the contribution from other deltas because they are 0 in the interval minus delta by 2 to minus t naught by 2 to plus t naught by 2. So therefore, you have delta of t into e power minus jk omega naught t. But what is this? This is basically shifting property, right? Using shifting property, this is same as, what is shifting property? First, we recall that integral x of t into delta of t over dt is same as x of 0. Oops, it's nothing but x of 0. This is our shifting property, or more generally what we wrote is x of t into delta of t minus t naught into dt is equal to x of t naught. This is what we wrote. Now I'm saying t naught is equal to 0. Okay, this is basically shifting property which recall from previous classes. Therefore, put t naught equal to 0, and that's basic. Why? Because this is only delta of t. This one is delta of t. So that means it is t naught is equal to 0. Therefore, it becomes x of 0. And the x of 0 is what? Whatever is multiplying. So here x of t0 is whatever is multiplying delta of t. So it is e power j0, which is equal to 1. So it is 1 by t naught. So ck is equal to 1 by t naught for all k. This doesn't depend on the small k for which you're computing the Fourier coefficient. Therefore, your x of t, and this holds even for k equal to 0, right? Because there is no 0 by 0 form coming here. Therefore, x of t is equal to 1 by t naught summation k equal to minus infinity to plus infinity e power jk omega naught t, where omega naught is equal to 2 pi by t naught. So in fact, many places we will use this expression as an alternative representation of this summation over delta functions. Okay, because both are same only, just that we are representing that in a different way, in a Fourier series way. This is a complex exponential Fourier series. Now, if I want to understand the trigonometric Fourier series, where x of t is equal to a naught by 2 plus sum over ak cos k omega naught t plus bk sin k omega naught t, where k runs from 1 to infinity. And 2 by t naught into integral minus t naught by 2 to plus t naught by 2 x of t cos k omega naught t dt. So x of t is nothing but in the interval minus t naught by 2 to plus t naught by 2, only one impulse function exists, which is delta of t only. You will not have delta of t minus 2 t naught or delta of t plus t naught. Nothing will be there because within the interval minus t naught by 2 to plus t naught by 2, all these guys take the value 0. Therefore, only delta of t will be there. And again, by shifting property, this is same as 2 by t naught into cos 0, because this is delta of t into x of t will be equal to x of 0. So with cos 0 is 1, so it's 2 by t naught. Similarly, so in particular, um, okay, this is only for ak, for k equal to 1 to infinity. But for a naught, you have this as the expression 1 by t naught integral minus t naught by 2 to plus t naught by 2 x of t. But x of t will be delta of t, so this integral will be equal to 1. So this will be just 1 by t naught. And bk will be similarly given by 2 by t naught integral minus t naught by 2 to plus t naught by 2 x of t sin k omega naught t dt. Okay, and just x of t is delta of t. because only the delta and the t equal to 0 contributes to this integral, because only that impulses exist in minus t naught by 2 to plus t naught by 2. Other impulse don't come inside this interval. So it is sine k omega naught t. And similarly, this is nothing but 2 by t naught to sine 0. But sine 0 is 0, so it becomes just 0. Therefore, what it says, it has only cost terms. Letting all values, x of t is equal to 1 by t naught plus 2 by t naught into 1 by t naught. Why? Because a0 was 1 by t naught and ak was 2 by t naught, and summation over k equal to 1 to infinity cos k omega naught t, where omega naught is equal to 2 pi by t. Now this is trigonometric Fourier series. So again, you see that only cos terms are there, no sine terms. Can anyone tell me why no sine terms? I will show you the figure. Can anyone tell me why no sine terms?
It might be even function, so even terms are there
Exactly.
and odd term are die out.
Correct. Exactly. You see, this x of t is an even signal, right? This is actually an even signal. You put t is equal to x of minus t, same as x of t for this example. That's why if it's an even signal, you should not have any sine component, because sine is an odd signal. You cannot write one even signal is equal to some function of odd signal, right? Therefore, sine terms will never appear in the trigonometric Fourier series representation of an even signal. Similarly, if the actual signal is an odd signal, in the trigonometric Fourier series representation, you will not have cos terms. Suppose you can try this at your home. Now, instead of this delta being here, maybe I do something else, such that I create an odd signal out of these impulse train. Then work out the Fourier series formulae and check that it will only contain sine terms but no cos terms. Okay, fine. So that's basically what I had planned for today. What I will do is, okay, we'll stop Fourier series with today, because we have I think we have done a lot in Fourier series. Next class we'll start problems on Fourier transforms. Okay, and one more announcement is that next week I will not be available on Friday. The class will be on Thursday. The NPTEL will basically be sending out an official intimation of that. It will be on Thursday, same time, 6 to 8 p.m. and same link as what you're attending from. Okay, so same time, same link, but on Thursday, not on Friday. Are there any doubts?
No, sir.
Okay, so don't forget that next week it is on Thursday, not on Friday. Okay,
Thank you, sir.
so yeah, sure. Then we'll meet next week. Thank you. Yeah, thank you all.